So, RF transceiver design, we are discussing about the inductors, passive components. We in the last class we have started understanding the on chip inductor, and we discussed about the spiral inductor. Now, in this class we will see more detail about the inductors and the transformer as well. So, here in this lumped element we are discussing about the modeling of spiral inductor. So, when you laid it out the spiral inductor, so if this is a spiral which is made like this, and then what will happen that there is a one metal, this is a one connection, and the if this is a metal 6 and then there is a metal we need to trace it out from metal 6 to metal 5. So, we need to connect it via, and then another metal we should use to do the connection bottom, and due to this there is a capacitance which is generated, that is a Cs, and that is why this Cs is coming here. There is a oxide layers that will provide the oxide capacitor. Even if more detailed modeling, there is a resistance due to the substrate below, here also can be added. So, it is depend upon how the measurement is, how measurement and models in order to make the models more accurate, there are more and more parameters will be added. But this is a widely used pi model, and in this there are capacitors, resistors and inductors. So, now we will go for the figure of merit of inductor. So, one of the figure of merit of inductor is the quality factor. So, we already have seen in the last class, quality factor is nothing but that is energy stored by energy lost per unit frequency omega, and that we already also have defined that if you have impedance Z in, then we can also write a Q which is equal to imaginary part of Z in by real part of Z in, or if it is Y in, then it is imaginary part of Y in by real part of Y in. Now, based on the model, we can write the quality factor Q, because there are many RC component, is a function of LS, RS, CS, Cox oxide capacitor, silicon substrate resistance or substrate capacitance. So, it is a quality factor is a function of all these parameter, and it is you can get by using this model. If you want to find the quality factor, you just consider it as a black box, 2 input, find out the Z in, and then plot the imaginary Z in by real Z in, you will get the quality factor Q. Another important parameter is a self-resonant frequency. So, what is a self-resonant frequency? So, frequency at which, that is FSR, frequency at which inductance of spiral inductance of spiral resonant with its own capacitor. So, because of the capacitor, you see here, because of this capacitor there are multiple capacitors, and that will because of that capacitor inherently there in the inductor, there is a one frequency, at one frequency it will resonate, and that frequency is called a self resonance, because we should not use our inductor at that frequency, because it is resonating, it will not give you any inductance at that frequency. So, if you see, uh, mostly real inductors, so the frequency at which the inductance of spiral inductor resonates with its capacitive parasitics, and real inductors have a capacitive parasitics and real capacitor have a inductive parasitics. So, in reality when we get the inductor which is designed, always there is a capacitive parasitics, and because of this capacitor inherent there in the inductor, it will be resonate at one frequency. And even the same thing is for capacitor, there is some inductive parasitics, and that tank circuit has a both inductor and capacitor. So, if you try to plot the quality factor Q versus frequency, and if it will start increasing, at one point of time it will start decreasing, and it will touch to the, and if we consider if it is starting from 100 megahertz, it is the center frequency is, let us say, if this is 1 gigahertz, this is 5 gigahertz, and this is a 10, or at this frequency if it is a 20 gigahertz. The Q is, let us say, 1, 2, 3, 4, 5. So, at one frequency of a desired frequency you will have a maximum Q. So, mostly the below this frequency it is more inductive. After the means when quality factor is reducing, it is more capacitive, and the frequency at which your quality factor becomes 0, that is a called a FSR, that is a self resonant frequency FSR, and in this case it is a 20 gigahertz. So, we should always use a inductor in this below this range. So, that is widely considered because at higher frequency than this it is more capacitive, there is no use, we want a inductor, and at 0 at FSR, this is a FSR, at this frequency your Q is 0. So, that is also not useful. So, as FSR frequency inductance at FSR frequency inductance is a resistive. So, there is a Q is a 0. So, if we take one example, this is a metal stake drawn on the Keysight ADA software, in which you can do the EM simulation. Now, here this is a silicon substrate, and then various so there are if you see metal 1, metal 2, metal 3, metal 4, metal 5, and the top metal layer ML. So, it is a 6 metal layer process, and when you want to simulate the inductor, you need to properly put this metal stack, and if you have not kept it proper metal stack, then the effective epsilon r that is considered by or the all the substrate effect when EM simulation will do the simulation, it will not carry out the all the information, means it will not use the all the parameters that we want, and we might get wrong results. So, it is better to make the metal stack and as per the foundry has given. So, you also need to consider that what is the thickness. So, these are the conductor, you should get this information from foundry, what is the thickness of metal layer, what is the minimum width, what is the minimum space, and the distance between the substrate in terms of micrometer. So, in this example your epsilon r silicon is considered 11.9, doping is considered as a p type, and silicon resistive capacity is considered 12 ohm centimeter, and metal conductivity is a 5.8 e raised to 7 Siemens per meter. So, this is once you have put the proper parameters, then you can start simulating. So, the next is you need to draw. So, in this the design specification, if your width is 11 micrometer, so there is a width between this trace is 11 micrometer. The space between these two traces is 3 micrometer. There are 2 tons that we have used, and area is approximately 300 micro by 300 micrometer square. So, it is a 300 by 300. So, total area. So, then if you find out the effective L effective, so you can see there are 2 plots. So, you can see here if you try to compare the plot of L effective and the Q, up to certain frequency your inductor is a constant. So, you should use only this range. After there is a inductors is changing, because you will have a maximum Q at this point, that is a 5 gigahertz in this case, and then your Q is reducing. So, then it is starting more capacitive, and then means your here your inductance is increasing very high, and then you are getting at this point 0 inductance, and here also when you go for when it is a more capacitive. So, here it is more capacitive. So, this is more capacitive. So, there is a inductance is reduced, it is a negative. So, that is capacitive as I told, and at this frequency it is a 0, your Q is 0. So, mostly we should work the frequency which is less than this frequency, means where the inductance is constant. Now, we can also make a transformer by using a inductor. So, same method we can use a transformer. So, if we try to understand how the transformer works, so this is a basic of transformer. So, there is a L1 inductor L1. So, this is a primary inductor, it is called a P1. This is a secondary inductor, this is a S. So, this is P1 P2 the connection, S1 S2. This is a secondary inductor L2, and there is a mutual inductance M. So, there is a same inductance L1 and L2, and it is mutually coupled. So, the coupling factor of mutual inductor is given by K M divided by L1 into L2, and inductance L is already depend upon the how you are making the turns and number of turns and the space. Important is quality factor of each winding. R, that is resistance, winding resistance, and insertion loss. So, insertion loss between these two because of the substrate. So, mostly transformer are where the transformer are used, you can you already know the mostly it is used in balun to make a single ended to differential. So, in balun it is also used in low noise amplifier, in mixers, or it is also used in voltage control oscillators. So, it has various application. It will help you to get the single ended to differential output. So, here you can see this is a P1, that is a primary. So, if it is drawn primary, so this is a green color to do the connection. So, this red is a primary coil, and the beside there is a secondary coil, and there is a connection P1 and S1. So, this is a basic structure spiral, that is a planar transformer. Then there is a another way of transformer, making a transformer, is by using sideway coupling. So, here n is equal to 2. So, number of turns are 2, and it is a symmetric both this side. So, it is a symmetric structure. So, in the previous structure there is a possibility of mismatch from primary and secondary, but in this there is a symmetric structure. So, mostly symmetric structure is used between primary and secondary. So, mostly it looks, so P1, so how the P1 connection will be, it will be like this, and the S secondary connection will be like this. So, here your, in this case you require, it requires more metal layers. So, here the number of turns is 1, not because there is only single turn. So, number of turn is 1, but in this there is a number of turns are 2. And in this you require more metals. This is about the transformer, where you can also draw it like this. And if you want to model the transformer, it will be same like a inductor. So, you can also use a different metal layer. So, in this there is a metal, one metal is used, metal 1, no, top metal, this is a top metal, and there is a one metal below. So, but in the top metal there is a air, means, and in the bottom metal there is a dielectric. So, there is a mismatch is possible, but this is also can be, this kind of transformer are also available, and you can design on chip. And when you want to consider the model of transformer, it looks as the same. So, this is only difference is the L1 and L2, and there is a between, there is, because P1 and S1 is connected. So, there is a capacitor between primary and secondary. So, L1 this is R1, means RS 1, RS 2, this is L1 L2, then this is oxide capacitor, and all the capacitor resistance, silicon capacitor, CSI, RSI. So, this is a pi model of transformer. So, this is how the transformer is laid it out, and there is a mutual inductance between these two. This is a model which is used in the when we try to design the transformer. So, one more thing, that one more effect that I want to discuss, that is a we can also use the method of pattern ground shield, means how to reduce pattern ground shield. So, in order to reduce the eddy current loss, So, eddy current is in the form of a circular in the substrate. So, how you can uh, reduce this loss? So, we can cut this. So, because it is flowing in the circularly in the substrate, we can try to put the metal which is crossing this and crossing on other side, which will discontinue the flow and it reduces the eddy current. And we can also make the slots in the form of this pattern. So, this is called the pattern ground shield, and this will help us to reduce the eddy current loss, and it is drawn on the bottom layer. In many application this is also drawn by using the polysilicon. So, polysilicon also is used or metal in the ground to reduce polysilicon metal stacks in the ground to reduce the eddy current loss. So, its advantage is it will improve the quality factor Q of the inductor, but due to the many shielding like this, it will increase the capacitor, and due to increase in the capacitor, what will happen that your FSR, your FSR self resonant frequency will reduce. Frequency will reduce. So, when there is a inductor which is drawn at the top, at the bottom there is a pattern ground shield which is pattern ground shield. So, this is PGS is widely used in order to reduce the eddy current loss. There are other substrate loss and all which are already there, but this we can reduce by using this method. So, if we try to summarize, so here same example on ADS. So, we have seen the example of inductor in ADS. Now, same example is also there for the transformer. So, this is a transformer. So, here turns for P it is a 1, turns for S is equal to 2, line width is a 10 micron and line spacing is a 3 micron. There is a x and y dimension is this. So, what is the performance? Your inductance Ls and Lp is almost equal at the desired frequency. Your quality factor curve blue color is for secondary, red color is for primary, and then there is a coupling, magnetic coupling coefficient K, which is important. It is very difficult to get a coupling factor in the range of 0.9 or 1, but more than 0.6 can be achieved by using the on chip transformer. So, this is about the transformer, on chip transformer, and if we try to summarize the all the points. So, some of the points that overall LC tank Q is limited by Q quality factor of inductor. Never place anything beside closer to the spiral inductor, or use guard ring around the inductor. So, in order to reduce the noise coming, and external metal filling in the inductor area, extra metal filling in the we need to avoid the extra metal filling, and we should maximize the symmetry in order to increase the IQ. And if there are more layers, then there is a possibility that due to the VII your resistance will increase. So, we need to make sure that when we are using a stack, multiple stack of the inductor in order to improve the effective inductance, then we should be careful, your quality factor will reduce. So, the important parameters for inductor is the quality factor, self resonance frequency, and what are the losses that coming out of the inductor. So, thank you. This is all about the inductors on chip. We will discuss more about the capacitor and resistor in the next class. Thank you.